All right, let's get started, guys. So this is the video for Monday, October the 12th. This is our first day for our second grade-in period, the second quarter. So the second quarter will go from October 12th until December 18th when we release for Christmas break. So that's exciting. So this is a good time of the year. This is probably my favorite time of the year because we get Thanksgiving break and we get Christmas break, and here in about 6 weeks, we are expecting our next child. Little baby William will be here, so that'll be interesting and exciting. Um, let's see. I hope you guys had a great intercession. Whether you attended or not, I hope you guys got some rest and got to do some other things. Kind of take a mental break, spend some time with your family or your friends. I had a pretty good break. I got to do some things that I haven't gotten to do in a while. I got to get outside, although it was kind of hot. Um, but it's been a good week. My kids were still in school, so they did a lot of school. So I did do a lot of homeschooling where I had to help my son with his algebra and his English tests and stuff. And I had to watch them quite a bit this week because my wife had doctor's appointments and stuff. But it was good to spend some time with the kids. Um, don't really get a whole lot of time with them during the week, so that was good. So let's start with assignments that you guys need to do today. So today we need to do the warm up during class. That'll be our in-class participation. And then I've got an exit ticket that I need you guys to do. Um, I mean, if you do it by Friday, that would be fine. Okay. Assignments that are due today by midnight. So there are several things that I gave you guys before the break that I wanted you to do. The first one was the chapter 3 through 4 problem set homework. And I'm going to make another video where I go over that after I get them all turned in. Okay. And you guys can watch that and kind of flip through the questions that you need help with, and I'll go over them. Some of them are quite tricky. I'll try to explain them the best I can, um, but most of them are pretty straightforward. They are all AP level questions, so they're right on par with what we need. The NIMSY notes, there's two NIMSY notes that I gave you guys. One of them is Chapter 3, Part 2, which we assigned before but kind of left off, and so I need everybody to complete that as soon as possible. And then Chapter 6, NIMSY notes over thermochemistry, and that'll kind of get you ready for today's lesson. Other assignments is I'm going to give you guys Chapter 12 NIMSY notes on kinetics. That's going to be due next Monday because that's when we're going to start that chapter. All right. All right, so this week's calendar, today we're going to go over Chapter 6, Thermochemistry. I'm going to go over a lot of terms, a couple of calculations, kind of get us familiar with enthalpy and Hess's law, which is kind of some interesting stuff with heat. Wednesday is going to be PSAT testing, so I don't think we will have class Wednesday. I'm still waiting to hear from administration about how Wednesday is going to run because it's virtual and on campus face-to-face PSAT testing. So I still don't even know if I'm giving the test. So I haven't heard much. So hopefully we'll be getting more information very quickly. I did some PSAT testing training recently about how to give the PSAT and what's expected and all that. But I haven't gotten any word on like whether I'm testing or if I'm going to be a hall monitor or what I'm going to be doing that day and what my classes are going to be doing. I imagine everybody's testing all day. All right. That's usually how the PSAT goes. And then Friday, we'll be back in class as usual. We're going to finish Chapter 6, probably try to do some free response practice. I might have a practice quiz for you guys to do. And then I'll talk about the precipitates lab, which is going to be a take-home homework lab. It's going to be pretty easy. I'm going to give you guys a video kind of like I did before where I show you some lab that I'm doing. And I'm going to be mixing different liquids. So I'll tell you what's in each bottle. And then you guys will need to determine the formula and basically predict the product of the reaction. And then name the products. So the whole goal of the lab is to be able to predict the products of reactions for double displacement reactions. It's the main one in precipitation reactions. and then write the net ionic equations for them. So this is really good practice. It's also going to be good practice for naming ionic compounds, which is important. We are in the second grading, second quarter. So we're starting off fresh. Just about everybody did pretty well last quarter in our AP chemistry class. So let's keep it up. Let's keep it rolling. I'm happy with you guys. I think you guys are doing a wonderful job. The only tricky thing is just, keep teaching and learning as we're doing virtually with the challenges that we have with that. But I think we're doing better than I anticipated. We are a little bit behind, but not too bad. And I'll give you guys some things over like Thanksgiving break, something short, maybe a NIMSY packet to do. But I probably will not be giving you guys anything over Christmas break. To me, Christmas break is in between semesters. And so we've already finalized the grade for semester 1 when we go on that break, and we don't start semester 2 until after. So to me, that's not a time for any kind of assignments. But if you need something to work on during that period, I'll be happy to make something that you guys can do. That'll be optional. I would say at that point, you guys might want to start thinking about looking for a AP prep book. And my recommendation for this is to try to find something that is after 2015. So as long as it's dated after 2015, it should represent the exam that we will be taking. And the newer the prep book, the better, because it'll be closer to what we'll see on the AP exam. So maybe around Christmas time, if you guys, if you get bored, if you get bored playing with your Christmas presents and you need something to do, you can do some chemistry. You can go through a AP chemistry book. There is one book that's really good, and I think it's called what is it? 5 Steps to a 5 or something like that, and it's like 500 questions or 100 questions or something like that, and it's pretty good. I'm trying to remember what the name of the book is. Something to a 5, something like that. So that'll be good. And really, if you guys don't review over Christmas break, the best review period will probably be in February and March. Will be when we want to start trying to review. All right, virtual attendance. Remember that you guys are required to type present in the chat for attendance. So if you guys do not communicate with me through the chat or through the mic during class, then you are absent, okay? And so we're going to keep that for the second quarter. Students are graded on their daily participation. This is a major test grade, so students are required to complete brief assignments during class for credit, and then work that is assigned during class must be completed by the end of the day. And I'm kind of lenient on our in-class assignments because the content is difficult. And so if you need some extra time to get the warm-up done or to get exit tickets done, that's fine. Just try to get it done by the end of the day, and that's totally fine. Okay. Another thing that I want to mention about the second quarter, I need just about everything turned in through Canvas, just to make it easier for grading. Okay, so any kind of Google Slides or Google Documents, anything that's like that where you have to share it with me, I'm going to require all students to turn it in through Canvas and not just email me. All right, and that's going to help. And this is probably more important for my regular chemistry class because there's so many of them. With you guys, it's not that big of a deal because there's a couple. But I have noticed, and this is why I'm making this important. This is why this is important. I have noticed that sometimes when students share things with me, I usually get an email, but sometimes I don't get an email. And so things are being missed. And sometimes I have to go back and look through my Google Drive and search my Google Drive for that student's email in order to find it. It seems like 99% of the time, if you share something with me, it sends me an email to let me know. And so I check my email, I see that you turned it in, and then I can grade it. But I have noticed many times where it doesn't send me an email, and I don't know that it's been shared to me because I didn't get any kind of notification that it was shared to me. The only way for me to know that it was shared is to check my email with an email that tells me, or physically go in and search my Google Drive, which I don't usually regularly do. So let's try to turn in things through Canvas. We should be good with Canvas. We should be able to do all that. You guys are doing great with everything in Canvas. All right, so we're talking about Chapter 6. Chapter 6 is thermochemistry. It is kind of a pre-AP honors level review of thermochemistry, maybe a little bit of thermodynamics. And some of this kind of gets into AP level, but this chapter is almost just a pre-AP review of thermochemistry. And then there's another chapter that's more advanced, and it's thermodynamics, and it talks about enthalpy, entropy, Gibbs free energy. It talks about equilibrium and a lot of things like that, all related to do with heat and if a reaction will happen. Thermochemistry is kind of the basics. Okay, so let's talk about energy. Energy is the capacity to do work or to produce heat. All right, work is force times distance, and so when work is done, you can tell that something is happening. If I push on a book and I see that the book is moving across the table, I know that I'm using energy, right? And I'm doing work because the book is moving, right? And so energy is the capacity to do work or to do something, make something happen, or to produce heat. If I use energy to produce heat, then we can see that there's energy there. So what are some of the different types of energy? Well, there is potential energy. And usually this is gravitational potential energy in a physics class, where potential energy is equal to mgh. We don't use this equation much in chemistry. That's mass times gravity times height. And so if I have a ball a certain distance above the earth and I drop it, I can determine how much potential energy is stored within that ball. And we know it has stored potential energy because if I let that ball go, we all know that the earth's going to take it and pull it down. And so the potential energy is reflects that. Then there's kinetic energy, which again, this is kind of more of a physics thing, but it is important for you guys to know the equations. This is equal to 1/2 mv squared. So that's 1/2 the mass times the velocity squared. So however fast that object is moving. So we may not use these equations and substitute them in chemistry. You may need to wait to take physics to see that. And you guys have probably seen these equations before in your middle school science classes and stuff. But we may need to use these equations to see the relationship between variables. So they may ask you, what's the relationship between mass and velocity here? Or what's the relationship between the mass and the velocity and the kinetic energy? So we may see it with relationships, but not necessarily, a full-on word problem. Let's see, there's chemical energy. There's electrical energy. What other energy types of energy do we talk about? There's nuclear energy. So potential and kinetic energy, the main ones that we see. Potential energy is the energy of position, but potential energy in chemistry is chemical energy, and it is the energy stored in bonds. So potential energy in chemistry is the energy stored in bonds. So if I have a hydrogen molecule and I have two hydrogens attached to each other, there is energy stored within that bond that is keeping those atoms attached. And so that is called potential energy, or bond energy, which we'll talk about. Maybe not in this video, but maybe in the next one. Bond energy, so that's the energy stored between bonds. So if you break bonds, you need to put energy in to break them. And then if you form a new substance, the new substance that forms has lower energy than what you started with, and so energy must be released. So anytime you make bonds, energy is released, because the products have to have lower energy than the reactants. Otherwise, the reaction wouldn't happen. Okay, and we'll talk more about these relationships. So energy is a capacity to do work or to produce heat. Kinetic and potential energy are two types of energy that we'll see in here. Kinetic energy is the energy of motion. And so if molecules are moving, we can kind of study the amount of energy in molecules based on their state of matter. So if we have a solid versus a liquid versus a gas, we should know that gases have high kinetic energy. And that kinetic energy is reflected in the temperature. That's what temperature is. Temperature is a measure of the average kinetic energy of molecules. So they're going to have a high temperature in order for gases to be present, like water, for example. The only way you're going to get vapor, water vapor, or gas, water in a gas state is if it has a high temperature. And then solids have lower kinetic energy and have lower temperatures, or substances are solid at lower temperatures. Okay. The first law of thermodynamics, there's it's actually 4 of them. There's the 0th law, and then there's 3 of them. So the first one is the one that you've known since 4th grade science, and it's that energy cannot be created or destroyed. So the law of conservation of energy is the first law of thermodynamics. The total amount of energy in the universe is constant. And so we can have energy transferred from one form to another, but we are not creating energy and we're not destroying energy. There is a certain amount of energy in the universe, and anything that we do, any kind of chemical reaction, is not going to change that. So energy is just transferred from one form to another. Total energy in the universe is constant. All right, here's our 2 definitions of energy. Potential energy is the energy due to position or composition. Remember, it's stored in the bonds in chemistry. Kinetic energy is the energy due to the motion, which depends on the mass and the velocity of an object. Okay. So here is potential energy stored in the ball here. And if we let that ball go, then the potential energy, gravitational potential energy, because it's high above the floor, that potential energy will turn into kinetic energy. So as the ball starts to move and it accelerates, more and more potential energy is used up, and more kinetic energy is created until it hits the floor. There's the formula for kinetic energy. The mass is measured in kilograms. The velocity is meters per second. The unit is called a joule, and a joule is a kilograms times meters squared divided by seconds squared. This is kind of more important in physics. We don't really use this too much, but it is important that you guys know that the kinetic energy in a molecule is equal to its mass times its velocity squared. So that just knowing that it's the mass times velocity squared is really important in predicting the energy, or predicting the motion of objects like molecules. Because there's a relationship between kinetic energy and boiling points and rates of diffusion for gases. And so we'll talk more about this in gases. But so let's say you've got a chamber here, and you've got some holes, and you've got molecules all in here, all kinds of molecules. They're all hanging out, bouncing off the walls, right? And then you've got another chamber here, and basically these 2 holes is where the gases can go through, right? And so some of the gas will go through, and it turns out that since kinetic energy depends on mass, heavier molecules will move slower. That's important for diffusion. That's important for chromatography. If you guys remember when we talked about chromatography, how we had molecules or some kind of ink down here, and the ink travels up the page. Well, that movement is dependent on the mass of the molecule. So that's all about the kinetic energy. And how it also, in paper chromatography, it also represents how the phase, so the ink here, how the ink is reacting to the paper, or not the paper. So let's say this is ink here. It's also about how the ink is reacting to the solvent, because you're gonna, an example of this is taking a tissue paper, putting a permanent marker, and then putting a dot, and then putting that in alcohol or water. And so the interaction between that ink and that water, which is a solvent, or the ink and the alcohol, will depend on how far that molecule will move. And so, but it's also depending on the weight of the ink. So the mass is very important. And then it's a square of the velocity, which depends on the temperature. So the speed of these molecules depend on the temperature. And there's a saying in thermochemistry, and it's this: heat them up, speed them up. And this is most of this chapter. If you heat up molecules, you speed them up. The higher the temperature, the higher the kinetic energy. So if you heat up molecules, they will move faster. Heat involves a transfer of energy between two objects due to a temperature difference. So that's what heat is. Heat is, let's say I've got a cup here and I've got a cup here. Let's say that this one is 50 degrees Celsius and this one is 20 degrees Celsius, right? If I were to mix these two, essentially the extra heat from this cup would flow into this cup. Okay, and so heat is a flow of energy or a transfer of energy due to a difference in temperature. So there's two formulas or two symbols for heat. One of them is Q, one of them is delta H. All right, so Q is heat, and delta H is kind of more enthalpy, which is kind of related to heat. Heat, or Q, is energy that is used to increase the temperature. So Q is used to increase the temperature. So if I'm taking an object like a cup of water and I'm heating it and the temperature is increasing, well, the heat that we're putting in is going to be joules or kilojoules possibly if we have a lot of energy, and the symbol for that is going to be Q. Delta H, on the other hand, is the heat required to change phase. So you have to put energy into bonds to separate the bonds, or you have to put heat into water molecules to break the bonds. So if you have hydrogen, oxygen, so here's a water molecule. Remember that the oxygen is slightly negative and that's slightly positive. And remember how these are going to stick together with the polarity of the water molecule. And so there's a hydrogen bond there. We have to put heat to break that. So if we have water as a liquid form and we want to turn it into gas, we have to break these bonds so that the water molecules don't stick to each other. Because water as a gas is water molecules that are bouncing all over the room, right? They're bouncing off the wall and they're kind of chaotic. And they're separated from all the other water molecules. When water is in a liquid form, they are kind of sticky. The molecules will kind of stick to each other. And then when they're solid, it's a three-dimensional network of water molecules. So something like this, where it's attached to another one. And it's a big three-dimensional network. And I'm just kind of, this is kind of, you kind of get the idea. And we'll look at some structures. But it's a three-dimensional structure, essentially. Still has hydrogen bonding in it, though. And that hydrogen bonding is actually why when water is frozen, it's less dense than when it's liquid. That's why ice floats. It's because the hydrogen bonding kind of creates holes in the crystalline structure, and so it's less dense than liquid water, which is cool because most substances are more dense when they're in a solid state, which makes sense. All right, what is the sign of heat when it is released? It's negative, and then when it's absorbed, it's positive. So let's look at that. Well, we've got it in here somewhere. Where is it? We'll look at that. When it is released, it is negative. So released, we say that Q is negative. And then when it's absorbed, Q is positive. So we can release energy from the substance, or release energy from the system, or we can absorb energy. And so the signs are important. Work is the force acting over a distance, and it's a transfer of energy. Okay, we'll see an equation for work here. It's not that common, and it's kind of simple and kind of more for regular chemistry, but we'll look over it. Temperature is a property that reflects the random motion of particles of a particular substance. It is equal to the average kinetic energy of the molecules. Okay, so the kinetic energy increases as the temperature goes up. Heat them up, speed them up. If you cool the temperature down, those molecules are moving less so. They're moving slower. They're sluggish when they're cooler. Those molecules also move slower the heavier they are, depending on the molecular weight of the gas. All right, there's two types of reactions when we talk about thermochemistry. The first is called exothermic, and this is where heat is released. So what happens as an exothermic reaction occurs is energy flows out of the system. Potential energy is changed to thermal energy. So that means that we're taking potential energy stored in the bonds, and it's creating heat. So heat is released. And then the products will have lower potential energy than the reactants. So here's a reaction. This is actually octane here, this guy. So this is like gasoline. This is like the main ingredient in gasoline. We take some gasoline, we take some oxygen, we ignite it somehow with the spark plug or with the lighter, and boom, we get CO2 and water, and we also get heat release. So we can write reactions like this where we actually show heat as a reactant, and it kind of is. It's another. It's not a substance, but it's energy that's released, and so we can write 5,076 kilojoules. When it is written on the right, it is energy that is released. All right. And then we could also write it this way. So we can say, okay, here's our reaction. Same thing. 2 moles of octane are going to react with some oxygen, add some heat, and boom, we get this. We can also write it like this. We can say that the delta H for this reaction, the enthalpy for this reaction is negative that much, and that means that energy is released. So delta H is always negative when energy is released, and that's called an exothermic reaction. So maybe some of these terms you guys have heard, but I imagine you guys didn't get much thermochemistry last year because of the schools closing. So this is a good review. So if there's anything here that's not making sense, please let me know. I'm trying to go at a basic level, assuming that you guys have never seen thermochemistry. So if it's an exothermic reaction, energy flows out of the system, potential energy is changed to heat. The products have lower potential energy than the reactants. So we'll look at graphs where we'll see this. We can show heat as a product. If it's an exothermic reaction, heat will be a product. That's why it's right here. Or we could show the enthalpy for the reaction as a negative number. So if it's negative, that means that heat is released. Enthalpy is the heat change associated with a reaction. Okay. The unit for enthalpy is kilojoules per mole of reaction. So what this means is that based on the reaction coefficients, if I have 2 moles of octane, 25 moles of oxygen, based on the numbers in the reaction, that's what this says, we're going to produce this much heat. Okay? And only that much. Only 2 moles of octane, 25 moles of oxygen. When you have exactly that much that reacts, you will get this much heat produced or released. Right? It's going to be released from the reaction. Okay. And the products will have a lower energy than the reactants. So these products here will have lower energy in their bonds than they did before. And you can think of it this way. This is a complicated molecule. There's 2, 3, 4, 5, 6, 7, 8. So this is what this molecule looks like. And as you guys can see, it looks like a branching hydrocarbon. And it's got some structure to it. It's kind of interesting, right? This molecule has a lot of order to it, right? And so it's going to have a lot of potential energy stored in these bonds. There's a lot of bonds here, a lot of energy. So when you break these bonds, you release that energy. And that's why gasoline is so good at doing what it does, because you break in these bonds. And so you break these bonds, you make simpler molecules, right? CO2 looks like this. There's a couple bonds there, but I mean, not much. You make 16 molecules of that for every 2 of these. And so this has lower potential energy. There's bonds there, but not as many. And then here's water. And I guess I could show the extra lone pairs on the oxygens here. So these are the 2 products here. Just by looking at the molecules, we can tell that they have lower potential energy because there's not as many bonds that need to be broken. Okay, so here's a reaction. So here is an exothermic reaction. This is our y-axis. It is energy, or change in E. And then this is reaction progress, which means that as you follow it, that means that the reaction is occurring. So it's kind of like time, but it's always going to be reaction progression or reaction progress, which is on the x-axis. And that just means that this is time 0, and this is kind of when it's done, when the reaction's finished. And so we start with the reactants here, A plus B. So let's write our reaction. A plus B will make C. So here's our reaction. A plus B are reactants. They react together. There is an initial bump that you have to go over before you can create the products. Okay, and this is called the activation energy. And so with the example of burning gasoline, the way that you get over the activation energy requirement, or to get up this energy hill, is to ignite it, add a source of energy. So add a match or a lighter or a spark plug in your car, and you can cause the gasoline to start burning. And then once you get over that hump, then you can go down. It'll go downhill from there, and you will quickly start producing products. And then down here are your products. And so this is your level of your reactants. This is your level of your products. Okay, and then this is the difference between them. Right, this is A plus B right here as well. This is C right here. And so that difference in energy is what we call enthalpy. It is the energy of the reactants compared to the products. All right, and this is going to be negative. Why is it negative? We started right here at this level, and look at the energy when we're done. It's down here. So the energy was up here, and we go down. And so that means that the energy is lowering. It's getting smaller. Right? Let's say if this was 20 kilojoules per mole, just for example. This is 10 kilojoules per mole. Well, the change in energy is 20 minus the 10. And so we get a negative 10 kilojoules per mole for delta H. And so that's why it's negative, and that's what delta H is. This is what enthalpy is. So this is what exothermic reactions will look like. The reactants will have more energy than the products. And so heat has to be released. Okay. Endothermic reactions are the opposite. This is where the reaction will absorb heat. So heat is being put into the system. So energy flows into the system or into the molecules. heat energy is changing into potential energy. And so maybe what we're doing is the opposite. We're taking elements and we're adding some energy, and then we can create a more complicated product that has more potential energy stored in the bonds. Another example of an endothermic reaction, and the most common example, is change of phase. If you take water as a liquid and turn it into water as a gas, that requires energy that you have to put into the water molecule, into the hydrogen bonds, to create gas water molecules. And so that you have to put energy into the system or into those bonds, and so that's called endothermic. The products will have a higher energy than the reactants. So this guy has higher potential energy than these two. And it does. It's got more bonds. Let's see the structure of this guy. This is ethane, a simple hydrocarbon. We call them hydrocarbons because they have hydrogen and carbon. And so that's the structure there. So look at all those bonds you got to break to separate the C and the H. And so that's a lot of energy there stored in those bonds. And the energy here is on the right side of the equation. I'm sorry, it's on the left side. So energy, the kilojoules per mole, or just kilojoules, is on the left side of the equation. Or we can write delta H as positive. So this is where energy is required for the reaction to occur. Energy is going to be put into the bond, into the bonds. So here's our reaction. Again, this is energy here on the y-axis. This is time. Our reactants are here. Our products are here. C is our product. So the reaction again is A plus B makes C. This is just a generic equation to kind of make this simple. As soon as we start the reaction, we add energy. Put energy into those bonds. The energy of the molecule, the energy of the system goes up. And then you still have some activation energy. This is called activation energy. Not sure if I mentioned that. This is the energy required to get the reaction started. Because you can't make products until you put enough energy into it, and then you can make your products. And actually what happens is the reactants start to fall apart, and you get somewhere right up here, right when you get to the very top of this point, you make a hybrid. The reactants start to kind of fall apart, and they start to form the products. And so it forms what's called a transition state, which is something in between the reactants and the products. And so it's right in the middle. It's a little bit of both. And so you'll start to form those products. And we'll talk about this in kinetics. That's why we have to do heat before kinetics. And a lot of teachers don't do heat, at least in Garland anyway, which it's confusing to me, but we have to talk about thermochemistry before you do kinetics because they are related. Because all of these heat terms and all of this heat concepts will feed into kinetics, because the kinetics is the rate of which reactions occur, which depends on the energy changes in a reaction. Okay, let's see, what else did I want to talk about here? Let's change the color here. So here is the reactants. Let's say the energy is there. Let's say that we're going to start with 10 kilojoules per mole for our reactants. And then here's our products up here. Let's say that this is 50. Oh, I guess I can't do, well, it's going to be joules as well. Oh, it is kilojoules. Kilojoules per mole. So up here they're 50, down here they're 10. So our change in heat, our change in enthalpy is 50 minus 10, which is 40 kilojoules. And as you guys can see, this is positive. And that's because you start down here and you go up to here. And so that is an increase in energy. So that's your delta H right there. So we need to be able to look at these graphs and determine whether they're endothermic or exothermic, whether their heat is released or absorbed, and then we need to be able to compare the amount of energy stored in the reactants versus the products. So in this case, the products have higher energy than the reactants. And energy is absorbed into the bonds. That's endothermic. Okay, there's two different concepts here that we've been talking about. There is the system, which is our reaction, okay? So imagine doing an experiment in the lab, and you've got a cup of water, and you're studying, I don't know, the change in temperature of that water. You're measuring, you're adding some heat, and you're observing the temperature change. Or maybe you're going to boil the water or freeze it. So that's what you're studying, okay? You're studying this cup of water, and that is called the system. And then the surroundings is everything else. And so when we study thermodynamics, we study whether energy is going into or out of the system. Okay? So if it's positive, we say that energy is going into the system. So that's positive delta H or positive Q. And then when energy is leaving, we say that it's negative heat or negative enthalpy. Okay? So the system is our chemical reaction, whatever reaction is occurring. And matter cannot go between here and here. Atoms are not able to travel between the system and the surroundings, but energy can. So this is what we call a closed system. And this is how we do our reactions. Okay, this is what we're going to assume. We're going to assume a closed system, and that means that mass cannot travel between the systems and the surroundings, but energy can. There's also something called an open system, which is different. And then there's another one. What was it called? Open, closed. There's one more. I can't remember what it is off the top of my head. It's more of a physics thing, though. But what we're studying in the lab, our experiment is our system, and this is the molecules, what's actually being, what's actually participating in the reaction. And then the air around this cup is the surroundings. All right, internal energy of a system is the sum of the kinetic energies, sum of the kinetic and potential energies of all the particles in a system. So we can write it like this. Internal energy, or change in energy, is equal to the change in kinetic energy plus the change in the potential energy. Or more simply, we can just write energy of a system is equal to kinetic plus potential energy. And then if we're doing physics, then that energy total can be equal to 1/2 mv squared plus mgh. If we're doing more of a physics discussion, a little bit more advanced. If you plug all of the terms in there. So that's internal energy, or the overall energy of a system. It's equal to the kinetic and the potential energy. What is the energy stored in the bonds? And what is the energy associated with how much motion that object has? All right, I'm going to take a quick break because I need to get something to drink. So give me a second, please. Okay. Energy is also equal to the heat plus the work. All right, so energy is equal to kinetic energy plus potential energy, as we said before. Energy is also equal to the heat plus the work that can be done. Q is heat, especially when the temperature is increasing or the temperature is changing. If you're heating up an object to change its temperature, we call it Q, and that's heat. And then there's work, which is W. And they're usually in joules or kilojoules. Thermodynamic quantities always have a number and a sign, and the sign represents the system's point of view. So if something is exothermic, we say that the energies of the system, what we're studying, is decreasing. So that means the energy is released. So here's our system. Energy is being released. And then if it's endothermic, then energy is going into the system. So that's positive Q. Up here is negative Q. That's a Q there. Looks like an A, but supposed to be a Q. So endothermic is where the energy of the system is increasing or energy is being added to the system. And exothermic is where the system's energy is decreasing or it is releasing energy. So here's our sign conventions. This is our system here. And so what would be out here? Our surroundings, the environment. So over here, these two, work is negative, heat is negative. That's exothermic, especially if we're talking about heat. And then over here, this is endothermic. Okay. Here's an example. So let's calculate the change in energy if the heat is equal to negative 50 and the work is equal to 35. So the change in energy is equal to the heat plus the work. So we're just going to add those two up. Change in energy is equal to the Q plus W, heat plus work. And we usually use a lowercase q, but for some reason there's a capital Q there. I don't know why that's positive. I don't know why that's capital. And then so it's negative 50 plus 35, which is negative 15. So we would have a negative internal energy here, which means that it's losing energy or it's releasing energy. All right, for a gas that expands or is compressed, we can calculate the work by this equation. So this is work. Work, and this is a real popular equation in chemistry, work is equal to the negative of the pressure times the change in volume. All right, so work is the ability to use energy or to push something or make something happen, to cause something to move or to cause something to occur. Pressure is the force of gas molecules. So let's say I've got a gas can here and I've got gas molecules hanging out here. These gas molecules are pushing and bouncing off the walls and flying around this container at all different directions very quickly. And so when they hit the container wall, the force that they push on that wall is the pressure. And so if these are moving faster and exerting more force, then it's at a higher pressure. And things can actually explode if the pressure gets too great. So it's pressure times the change in volume. How much is the volume changed? The units for work is a liter atmosphere, or an atmosphere times a liter. The unit for pressure is the atmosphere. 1 atmosphere is the weight of the air above your head. So think of here's the Earth's surface. Here's the like out here is space. Okay, so this is like the edge of the Earth's atmosphere. So here we are. We're hanging out. This is the air above us, right? And so that air is pushing on us. And that's pressure. And that is 1 atmosphere. The amount of pressure pushing down on us. Okay, and that's the standard unit for pressure, is the amount of air between you and the atmosphere above your head. That's 1 atmosphere. And then a liter is the unit for volume, so it's a liter. 1 liter atmosphere is equal to this many joules. Okay, and you don't need to know that relationship, but that's the relationship between a liter atmosphere and the unit for energy. right, which is joules or work, right? Okay. So let's calculate the work if the volume of a gas is increased from 15 milliliters to 2 liters at a constant pressure of 1.5 atmospheres. So what is the work that is done if the gas volume changes from 15 milliliters to 2 liters and the pressure is held constant at 1.5 atmospheres? So let's plug it in. Work is equal to negative P times the change in volume. We plug in the 1.5 for our pressure, which doesn't change. And then this will be our change in volume. How did we get that change in volume? What did we do? Let's take 2 liters. I'm going to do, let's see, 2, with the decimal there, I'm going to move it 3 times. 1, 2, 3. So that's 0.002 milliliters. We're starting from 15. Oh, that's 2 liters. Oh, I'm going backwards. 15 milliliters, and we're going to go to 200 milliliters. So what I meant to do is to take the 2 liters and move it 3 times this way so that I get 2,000 milliliters. So we're going from 15 milliliters to 2,000 milliliters. So we're going to do 2,000 minus 15, and we get this 1,985 milliliters. Again, move the decimal back over here, 1.985 liters. And that's our work. That is going to be negative. Okay, and that just means that energy is being released from the system. Work is being done. Work is being done by the system onto the surroundings. That's what that means. All right, at constant pressure, the term heat of reaction and change in enthalpy are used interchangeably. So heat of reaction and enthalpy can be the same thing at constant pressure. All right, so here's an example. For the reaction, 2 sodiums plus 2 waters makes 2 sodium hydroxides and H2. Here's our heat of our reaction. It is equal to negative 368 kilojoules per mole of reaction. Again, that means that for every 2 moles of Na and 2 moles of H2O that react, we're going to get this much energy right here. Okay. So calculate the heat change that occurs when 3.5 grams of sodium reacts with excess water. So we're going to take 3.5 grams of sodium. And so what we're doing, guys, is we're doing thermodynamics, right? Doing thermochemistry, but we're kind of mixing it with stoichiometry, and I think it's kind of fun. So we're going to start with 3.5 grams of sodium. I'm going to divide by the atomic mass of sodium. Why do I not have this one done in my notes? I have my notes here, but I don't see this one. Maybe this one was more simple. Yeah, I think I just printed I printed some of these, and that's just like the harder ones. So this is 23 grams of sodium and 1 mole of sodium. That's the atomic mass of sodium. So now I know that now we have moles of sodium. I know that 2 moles of sodium will form this much energy. So let's write that relationship. 2 moles of sodium will form negative 368 kilojoules. And it is mole per mole of reaction because it's this much in relationship to the 2. So that means that 2 moles of Na for every negative 368, which is what I wrote here. So that's totally fine. All right, and that'll give us the amount of energy change that occurs. And what do we get? All right, so 3.5 times negative 368 divided by 23 divided by 2. I think we should get negative 28. Negative 28 kilojoules released when this reaction occurs. So this is exothermic. And this heat would be negative, right? Which we already know that's negative. Let's see how I did. negative 28 kilojoules. So we can write our answer two ways, okay? We can write negative 28 kilojoules, or we can write 28 kilojoules energy released. Same thing. You can write it either way. It's probably easier to just use the negative. So we can say our answer is negative 28 kilojoules, or we can say 28 kilojoules is released. All right. All right, calorimetry is the science of measuring heat flow. We usually use a cup. And so this is like a styrofoam cup that prevents heat from flowing out of it. It kind of insulates it a little bit. And it's also got a lid, and you put a thermometer in it. And basically, we're going to change the temperature in this cup. So this is based on observing the temperature change when a body absorbs or discharges heat. So this is called the calorimeter. The unit calorie is actually a unit of heat, of energy. Think about food. Think about, look at your food. It doesn't have calories. That's a capital C. So there's one unit that is a capital C, calories, and then there's a little cal. Then there's also kilocal. So these are units of energy or heat. And so when you look at your food, a calorie is a unit of energy. And that's the amount of energy that you would have to burn, right? You can burn calories or use them up in your body, like when you exercise. So it's kind of cool relationship with food. Calorimetry can be used to find the delta H for a chemical reaction. This is the heat involved in a physical change or the specific heat of a substance. Okay. I think I'm going to stop here. So we'll get into this next time. I just don't want to go too long. I don't know how long I've been doing these notes. I wish I had a timer here. I should have started a timer. But I'm going to go ahead and stop because I don't want this to run over. So let me go back, make sure that you guys have completed the warm-up and the exit ticket for today, and then here is the assignments that are due today. And then between now and next Monday, I just need y'all to do the NIMSY notes. All right, guys, thank you. I hope you guys are enjoying thermochemistry.